Hello, in this video I'm going to solve the following problem for you. This is problem 2.12 from the book Classical Dynamics of Particles and Systems, 5th edition, Thornton and Marion. Let us read the problem together first. A particle is projected vertically upward in a constant gravitational field with an initial speed v0. Show that if there is a retarding force proportional to the square of the instantaneous speed, the speed of the particle when it returns to the initial position is v0 times v sub t divided by the square root of v0 squared plus v sub t squared, where v sub t is the terminal speed. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. Okay, so let us see what the setup is. So assume that this is the ground level, and then I shoot my particle from the ground level upwards, and let me consider this the y-axis. So on the y-axis I will have actually the y hat, the unit vector corresponding to the y-axis. So I shoot my particle from the ground level, it goes up, it comes to a halt mode when the speed becomes 0, returns back and hit the ground, and I want to calculate the speed of the particle when it hits the ground. And I want to show that that speed, let me call it capital V, I want to show that this is V node, this is the shooting speed, and Vt, which is the terminal speed, divided by V node squared plus V terminal squared. So this is what I want to show. So this is the speed here when the particle returns back. Of course, you know that if there is no air drag, then this speed would be exactly V node. Okay? Okay, so let me try to understand the problem together. Okay, so let us consider that my particle is now somewhere here, with its, and I will consider that this is its y coordinate. Yes, y coordinate of my particle. Two forces are acting on my particle. So that one of them is the force of gravity, of course. So the magnitude of the force of gravity is mg, but in this setup, it's pointing downwards. Of course, it's always pointing downwards, but in this setup, it would be negative y hat, yes? So this would be the vector force for gravity. But my retarding force is always acting in the opposite direction of the velocity of my particle. According to the problem, so let us consider f sub r for retarded. This is proportional to the instantaneous speed of the particle squared. So let us consider b, the positive number b is the proportionality constant. So according to the problem, it is proportional to the speed of the particle to the power of 2. Okay? So this is the magnitude of the retarding force. And I am using this v here for the magnitude of velocity, of course. This is called the speed, yes? So I'm using v for the magnitude of the velocity. And if I want to write it in the vector form, I write it in this form. I would say that this is always against the velocity. So I put a negative sign, then I put a v hat here. What do I mean by v hat? V hat is the unit vector in the direction of my velocity vector. And that is reasonable, because if my particle is going up, the retarding force is acting downward. When the particle is going up, v hat is pointing upwards, but I want to have my vector force vector to be downward. So this I put a negative sign. On the other hand, if the particle is coming back, then it means that v hat is pointing downward, because v hat always points in the same direction as the velocity vector. But of course, I know that the retarding force should act upward, yes? So then again, I need this model. So this is completely generic. It doesn't matter when the particle is going up or if the particle is going down, yes? What matters is this v hat. What is v hat? When the particle is going up, v hat is the unit vector in the upwards direction. So that is there is no difference between v hat and y hat. So this is y hat. When the particle is going up, let me just show it by this. And then, of course, it becomes minus v hat if the particle is going down. So this we need to know. So this is the unit vector along the velocity vector. And now, if I ask you what is the total force, of course, the total force is the sum of these two vectors. I need it for the second law, Newton's second law, yes? So this becomes minus mg y hat minus bv squared v hat. And remember, v is the speed. So this is independent of the direction of the particle. Is it going upwards or is it going downwards? Yes? But let us also understand what is the magnitude of this terminal speed. Okay, terminal speed is achieved when the total force acting on the particle is actually zero. Yes? So if I want to understand what is v terminal, so I put v total equals to zero vector, and then it means that, and then at that time, the speed is the terminal speed. So it means that minus mg y hat minus bv squared v hat is supposed to be equal to zero. But of course, we know that this happens when the particle is going down. Yes? When I shoot the particle upwards, there is no terminal speed involved, so it goes higher and higher so that it reaches to speed zero and then comes back. In the way coming back, I will reach to the, if I want to reach to the terminal speed, which of course technically or mathematically I will never ever reach the terminal speed. If you have seen the calculations, it needs infinitely a long time to achieve that one. So it means that when I am coming back, I'm getting closer and closer to the terminal speed, but I will not ever achieve that one because achieving the terminal speed needs infinitely long time. Yes? Okay, but in that case, I will change this v to vt and try to solve that problem. When it is coming back, v hat is minus v node. Sorry, v hat is minus v hat. V hat is minus y hat. And if I put it here, this becomes positive y hat. And then I solve this equation. So this means that bvt squared is equal to mg, and then it means that v terminal is the square root of mg over b. And I don't need to be worried about plus minus sign here because this is a speed, not velocity. So that's the terminal speed. Now I want to solve my problem, but I have to divide my problem because you see that my force is dependent on v hat, and v hat, depending on which direction my particle is moving, is either y hat or negative y hat. But before that, because I want to write the second law of Newton in this form, dv, this is velocity, not the speed, divided by dt. So equals to f total, yes? This is the equation that I have. But before starting, let me calculate this part a little bit, write it in a different way. I want to show that this is not sensitive to the direction of the motion, yes? How? I would say that, what is the velocity vector? The velocity vector is the speed multiplied by v hat, which I defined up there. So this means that if I calculate the derivative of v with respect to t, I have to take the derivative of this with respect to t. But of course, this is either y hat or negative y hat, and the derivative of v hat turns out to be 0. And then it means that if I want to differentiate it, I only differentiate the speed. And then I put a v hat here. Okay? But now I want to write it in this form. Instead of dv dt, I would write dv dy. Y is the coordinate, the y coordinate of my particle, multiplied by dy dt, and then I will have v hat. So be careful, dy dt is not the speed, is the velocity. But, so this is why I cannot write just v, because I am using v for speed, not velocity. But if I ask you what is the relation between speed and this quantity, I would say that this is equal to the absolute value of dy dt. So the magnitude of velocity is a speed. Yes, and then this becomes equal to dy dt if my particle is going up, y, because when my particle is going up, dy dt is positive, y is increasing by time, and it is equal to this positive speed. And then if my particle is going down, if I just write dy dt, that is not correct, because here when the particle is going down, y is decreasing by time, and it cannot be equal to this. So it means that if I want to fix it, I have to put a negative sign here. So in principle, if I ask you what is dy dt, you will say that this is either plus or minus v, depending on which direction the particle is moving. Positive for upward direction, negative for downward direction. Okay, so it means that if I want to continue that, I would write dv dy, and instead of this quantity, I can put plus or minus v depending on the direction. And then v hat also is equal to y hat or negative y hat exactly accordingly to the direction of motion. Not the other way around. That is the good point, yes? So it means that when my particle is going up, I have to pick the positive sign here. When my particle is going on, I have to consider the positive sign here. And if the particle is going down, this becomes negative, this is also negative. So it means that at the end, this is not sensitive. This quantity is not sensitive to the direction of motion. In each case, it becomes just v dv dy y hat. And if you tell me what v is, I would say v is a speed, not velocity. Okay, so then I multiply that quantity by m, which is not sensitive to the direction, and I equate it with the total force. Okay, so I would say this second law will read like this: mv dv dy f total. But f total is sensitive to the direction, so it becomes m minus mgy minus b v squared v hat. So this is the equation. Okay, sorry, I have to put y hat here as well. Okay, so this means that this is equation that I have to consider and solve. This is my differential equation. Okay, now I consider two cases. The particle is going up. If the particle is going up, what happens? Going upward, yes? In that case, v hat is nothing except y hat. So if I put y hat here, I have y hat here, I have y hat here, dropping y hat, then I will get mv dv dy is equal to minus mg minus bv squared. But there is no track of velocity in this equation. Every v that you see is a speed. Okay, now I divide by m, for example, here, so I will have v dv dy equals to minus, let me factor a minus sign out as well, so it becomes g plus b over m v squared. Okay? Yes, I can also, by the way, I can also factor a g out. So why this is good, so let me just do that. I factor a g out, then it becomes 1 plus b over mg v squared. But this quantity, if you see, is the reciprocal. So here you see that 1 over vt squared is nothing except b over mg. So that b over mg that appears here is actually the reciprocal of the square of the terminal velocity, terminal speed, sorry. So then it becomes minus g 1 plus v squared v terminal squared. And now I want to solve that problem, yes? So how should I do that? I have to solve the differential equation, so I will write v dv and I divide by 1 plus v squared v terminal squared, yes, and then I will have minus g on the right, and then I have dy coming from this. So this is my differential equation. So I have to integrate. So integrate, what are the limits of integration? That's a constant, I pull it out. So I integrate from this ground level up to the height, the maximum height. So let us consider that the particle goes there, and the maximum height, let me call it capital H. So I integrate from the ground level up to that maximum height, which I don't know what that is. But then in that case, the shooting speed, when the particle is at the ground level, the shooting speed, according to the problem, is v node. And then it reaches to a halt when it is in the maximum, so it means that the speed top there is 0. Okay, and then I have to integrate this, but this integration is easy because forget about these are constants and the derivative of this appears somehow here. So that's a very standard simple integration. So if you do integrate that, it becomes ln of absolute value of 1 plus v squared over v terminal squared, but I have to adjust it somehow here. So that it will give me that. So it becomes v terminal squared over 2, yes? Let us double check. If I differentiate this, this will go into the denominator, then I have to differentiate it in the numerator. So it becomes 2v divided by v terminal squared. 2 and 2 will cancel, v terminal squared will be cancelled, and v will be left, which I needed. So everything that I have done is right. On the right-hand side, so by the way, I should calculate it between v node and 0. I'm not allowed to interchange them. You have to respect the order, of course. On the other side, I will have minus g, y, and it goes from 0 to h. Okay, if I substitute these, what I will get the maximum height. Yes? So if I put 0 here, it becomes ln of 1, and ln of 1 is 0, yes? And then I have to put v node here, but I will get a negative sign, so it becomes minus v terminal to the 2 divided by 2, ln absolute value 1 plus v node squared divided by v terminal squared. Absolute value, but of course everything is positive, so let us not bother about absolute value. We can replace it with paired brackets. Okay, on the right hand side I will get minus gh. And I divide by minus g, and finally I get my h. So h is vt squared over 2g ln of 1 plus v node squared divided by v terminal squared, yes? So that is the maximum height achieved by this particle. V node is the shooting speed and vt is the terminal speed that can be calculated using this formula. Okay, now my particle is up there and it starts returning back. So I have to solve more or less the same problem, but for the particle going downwards, yes? So that going downwards, the only difference is that I showed you that the left-hand side of the Newton's second law is not sensitive to the direction of motion, and it's always this one. But the right-hand side depends on the direction of motion because of v hat in the form of the total. So here, v hat is negative y hat this time. So if I want to show going downward, so what happens in this case, v hat is minus y hat, and then I write my differential equation. The left hand side is not sensitive, so let me just write it as before, dy y hat, but the right hand side is minus mg y hat, but then you see this part becomes positive b v squared y hat. Okay, so then this tells me that I can use the same trick, so I divide by m, I will get v dv dy, and on the right hand side I will get minus g, I'm dropping y hat as well, so it is minus g and then plus b over m v squared, and that is exactly the same story. So if I factor minus g out as before, so it becomes 1, but minus v squared over v terminal squared. So I will get that. I factor the negative side, negative g out, then it becomes b over mg, and then I use that one again, but I will have the same scenario but with the negative sign. Then I have to solve this differential equation. So let me move it on. So if I want to solve that, I use the same trick. So I will have v dv, and here I divide it by 1 minus v squared over v terminal squared is equal to minus g dy. Yes? But this time, the particle is up there, it's in the maximum height, and I am interested for the speed of my particle when it hits the ground. So I integrate the original position, the initial position is h, it reaches to the ground level. The initial speed top there is 0. It is supposed to reach to v, yes? And then I have to calculate and find v. Okay, but let us do the integration. The integration is more or less as before. So this becomes, so the integration is exactly as before that you see here. So it becomes minus vt squared over 2 ln of absolute value of 1 minus v squared vt squared. And here you will get minus gy. It goes from h to 0. And here it should go from 0 to capital V. Okay, so then again what will happen? So I will have minus, and let me double check. If I integrate, if I differentiate this, this will go into the denominator. I will get minus 2v divided by that one. That minus will cancel this one. Vt squared will cancel that one. 2 will cancel this one, and then 1v is left. So that's okay. And then if I calculate that, it becomes minus vt squared over 2. Then I will have ln. Instead of v, I put capital V. And instead of v, I put 0. When I put 0, ln of 1 is 0, so I don't need to bother about that. So it becomes v squared over vt squared. And on the right-hand side, I will get positive gh. So here, this is speed. Is the speed when the particle hits the ground, and this is the terminal speed. Yes. So when the particle is actually coming down, then this terminal speed, because the speed of the particle starts increasing until it reaches to the terminal speed, and after that there is no increase in speed. But if you have studied chapter 2, you will see that for reaching to this terminal speed, I need infinitely many times. So it means that v, on the safe side, I'm on the safe side, v is always smaller than vt. So this fraction is smaller than 1, so 1 minus that fraction is positive. Again, I don't need absolute value signs. I can replace them with a pair of brackets. And then I calculate h from here. So what happens is that h is minus v terminal squared over 2g ln of 1 minus v squared over v terminal squared. So this is my h, okay? So I calculated h in 2 different ways. Or actually, I have 2 equations. Let me see if you are in the frame. If that is in the frame, let me see. I cannot see it so small. Yes, it is in the frame. So here you see that this equation is giving you h. This equation is also giving you h. And then let me make sure that I haven't made mistakes here. 0 and 2, yes, that's positive, so that becomes negative. And that's also understandable, yes, because this number is smaller than 1. Ln of a number smaller than 1 is negative, and that will compensate for that negative. I was a little bit worried about this negative, so I know that's okay. So now what I have to do, I have to equate them. So that h is vt squared divided by 2g ln of 1 plus v node squared vt squared should be equal to this quantity. So which is minus vt squared over 2g ln, this time y minus capital V, which is 1/3 divided by vt squared. Okay, so I can simplify that with that one, then I will get ln of 1 plus v node squared vt squared is equal to minus ln of 1 minus v squared vt squared. And I take this minus sign, if you don't mind, and I put a negative 1 as a power there. And then this ln is equal to that ln. Ln is a one-to-one function. So this means that 1 plus v node squared divided by vt squared is equal to 1 over this expression, yes? Okay, and then I am looking for this. So I interchange these two. Then it becomes 1 minus v squared vt squared is equal to 1 over. So let me take the common denominator here. So then I divide. So vt squared will go up. And then I will have v node squared plus vt squared here. And then what I do, I multiply. So I move this to the right and move this to the left. So it becomes 1 minus vt squared v node squared plus vt squared is equal to v capital over v terminal squared. But if you take the common denominator here, it becomes v node divided by v node squared plus v terminal squared is equal to capital V squared v terminal squared. And then I multiply by v terminal squared. And this becomes v squared. And finally, everything is a speed actually here. So then it means that v is positive, so I take the square root. It becomes v node vt divided by square root of v node squared plus vt squared. Yes? And that is exactly what is demanded in the problem. Okay. So I hope that this video is somehow useful for you. Until the next video, be safe and goodbye. Thank you.